in Dr. Bonomo's group in chemistry. Today I'll be going over the metabolic engineering of glycolipids outfitted with a chemical handle for a novel bioorthogonal click reaction. As an introduction into my project, we're going to go a little bit into the biological application. So bacteria have an outer membrane which is used as a physical barrier for protection. This barrier in gram-negative bacterial cells protects the cell from the outer environment it is in contact with. The outer membrane is the first point of contact and is the first mode of defense in bacteria. The outer membrane of bacteria is a bilayer in which the outer layer, which is composed of liposaccharides. A liposaccharide is made up of three very distinct units. These units are attached by an acyl chain, and they are lipids. A liposaccharide is just a glycolipid, which is a unique term for a sugar-containing moiety. As we dig a little bit further into my actual project, KDO, which is the glycolipid, which is a sugar on the lipid polysaccharide, is kind of our key molecule that we are studying. KDO is responsible for maintaining the negative surface charge on gram-negative bacteria, and gram-negative bacteria utilize KDO, and it can be visualized in the outer membrane of the bacteria. KDO is typically activated by an enzyme, and this enzyme is utilized by the LPS molecule itself. In the bacterial cell of the outer membrane, there have been many attempts and methods to try and label the outer membrane of the bacteria. A very recent and important new development involves the bioorthogonal click chemistry. Click chemistry has been utilized to mediate the labeling of the cell surface. Previous works include using a KDO molecular modified with a terminal azide group. This work provided a very valuable information due to the gram-negative bacteria uptake. The bacteria was able to take up the modified sugars and was visualized in the core of the LPS molecule. The azide was successfully studied and seen on the LPS cell surface. The azide can undergo a copper-mediated accessible click chemistry of the alkyne azide cycloaddition. The constraints to this type of click chemistry is the toxicity to the cell by the copper used in the reaction. Bioorthogonal reactions have crucial in understanding glycosylation cells, which in turn can provide visualization tools, therapeutic applications, and molecular imaging. A key component to click reaction is the ease and speed. The ability to modify functional groups and study their interactions on the cell level is critical in click reactions. The key part of my reaction and importance of what I'm doing is I'm developing key bioorthogonal functional groups through usual organic chemistry pathways. These small molecules, when they are utilized into the biological system pathways, undergo click chemistry. Typical pathways in the past have had several issues such as stability and delivery problems. A key component in my research is developing handles that can be further utilized in the click chemistry route and be visualized. We are essentially doing metabolic engineering. It's a great technique to add chemical functionality to a natural product. Many probes that are designed, they're very limited in their scope of testing bacteria. The aim of our group is to make bioorthogonal reactional handles that allow for hydrogen bonding interactions with the enzymes. These interactions with the azides and with the enzymes they interact with. Azides and propargyl groups can't engage in the recognition events. Our work is geared towards the utilization of hydroxylamine analogs, which are key because they are primed to engage in the retrocope bioorthogonal strain system reactions. Our group is responsible for investigating the bioorthogonal cycloaddition reactions. In previous works, the cyclooctene was investigated with dialkyl hydroxylamine. The key aspect of this reaction is the utilization of a pi system to form a charged intermediate capable of direct interaction with the bacterial cell. A critical issue with the azide modification in the alkyne is the size. The extra three components of the nitrogen chain does not incorporate without issues. That is why we are using the hydroxylamine that I'm currently synthesizing. In my research, I've done several synthesis routes, and I'm pretty sure they've been successful, but to make the KDO modified hydroxylamine, I have to characterize everything. So for future works, I need to characterize, purify, and modify the KDO analog. Characterization techniques will be NMR, IR, mass spec analysis, and I will be further incorporating these KDO analogs into gram-negative bacterial systems. Thank you for listening.